All right, this video is going to help us understand another of the conic sections. Ellipses are a conic section if you take two cones, two napped cones, and you slice sideways through a cone. You'll end up with an ellipse. Now, a way to construct an ellipse in 2 dimensions, well, there's various ones here shown on your screen. A lot of famous mathematicians throughout the centuries have researched ellipses because they're very applicable to what we do in the real world. Probably the most normal or kind of easiest way to understand ellipses is this string construction up at the top. An ellipse can be defined as a set of all points, the sum of whose distances from two distinct fixed points is constant. Or basically saying if we have two foci, right? Remember with parabolas we had what we called the focus. It was always inside the curve. On an ellipse there are two foci, again both inside the curve, and the distance from the focus to the edge of the ellipse plus the distance from that point to the other focus, or d1 plus d2, will always be constant. So as you notice as this set of strings here, if you imagine the blue and the red lines being a string, if you pulled that taut with a pencil and worked your way around, notice that the blue plus the red always stays constant right here at a total length of 10. Even though the blue might get longer, or the blue might get shorter, thus making the red longer, the total, again the sum, stays constant. So that's kind of a unique relationship for an ellipse. That's our locus definition, or the geometric way of defining an ellipse. Again, if both foci came completely together, that one string would just reach to the edge, and you would actually make a circle. And remember, the definition of a circle is all points equidistant from one focus, from one center. Well, in order to work with ellipses, we need a little bit more of a workable definition. Or an equation would be very helpful. Realize that an ellipse, and we're going to keep ours both vertical and horizontal, we're not going to kind of tilt them, but if an ellipse has a horizontal and a vertical axis of symmetry, if the major axis, the longer axis, is vertical, then your equation is up here at the top left. X minus h, again h being a shift to the left or right, x minus, y minus k being a shift up or down, h and k will define the center of our ellipse. The center will always be that point hk. Now realize that hk is not a point on our ellipse, it's just the point in the center of the ellipse. The points on the ellipse are defined again by those distances out to the edge. If we work our way straight up and down on that vertical major axis, we would call that our a value in our equation. Because y was squared and a is longer than b is always the shorter distance, the other direction. Because the longer distance is beneath the y squared, we're going to travel in the y direction for the major axis. Again, the b squared would tell us the distance we're going to travel from the center, left and right, because it's beneath the x squared. And remember, x always travels horizontally, left and right. C will be the distance from the center to the focus. The major axis has a total length of 2a. Again, center to edge is a. From vertex to vertex, as we call it. Again, those points at the ends of the major axis will be the vertices. From vertex to vertex, that's a length of 2a. 2b will be the length of what we call the minor axis, the axis traveling the other direction, that green line right now. And c, again, is focus to center, or center to focus. 2a would also be that distance d1 plus d2. Remember that we would technically travel, and let's take a look at that when we go over here to this side, because that b value, again, is going to be half of our green line. C is going to be, again, out to the focus, and A would travel the full distance. Well, the other kind of unique relationship is that B and C sort of form two sides, two legs of a right triangle. And if we actually took B squared plus C squared, it's a unique relationship. You would actually end up with A squared. A is that hypotenuse of that triangle, which sort of makes sense. Again, the distance from focus to point and point to focus is 2a. So again, A ends up being that hypotenuse of that triangle. Again, just kind of a unique relationship, but it brings about a very helpful formula as well. C squared, because C is one of the legs, is equal to A squared minus B squared. Very similar to a Pythagorean theorem, but note its subtraction. The hypotenuse squared minus one of the legs squared, right? We've subtracted it over, is equal to the other leg squared. So A squared minus B squared equals C squared. One last thing that we want to discuss when it comes to horizontal or to ellipses is what's called the eccentricity. The eccentricity of an ellipse is basically just a relationship of ovalness. If we take C divided by A, again, the eccentricity is C divided by A, we can determine how oval, how round an ellipse will be. Will it be closer to a circle, which would have an eccentricity of 0? The smaller the eccentricity or closer to 0, the sort of rounder it is. If E is 0.7 or 0.96, notice how oval it gets, very stretched out. And in fact, if C is exactly 0, as we said, it's going to be a circle. If C equaled A, if the distance to the focus was equal to the distance to the vertex, if C was stretched out to A, the side would kind of get pulled in, and basically you would end up with a perfectly straight line. So that's just an interesting fact about eccentricity. It's a way to relate, again, the roundness, how close to a circle versus how close to a straight line our ellipse will be. Again, the major idea for that is E equals C over A. Finally, just one last thing. Again, we talked about the vertical major axis. In order to switch that around to be a horizontal axis, such as over here on the right, you'll notice that the larger distance A is beneath X, the shorter distance B is beneath Y. That's the easy way to keep track of whether or not it's a horizontal or a vertical major axis. So with that, let's talk a little bit about details. If we want to find the center, vertex, focus, and eccentricity in order to sketch an ellipse, we just need to look at our equation and define a couple of major things. First of all, we want to look at the center. So looking at our equation right here, you'll notice that x squared and y squared don't have anything subtracted from them. That means that our center right now is 0, 0. A is always the larger number, so again 9 is greater than 4, which means that's a squared right there. A squared equals 9, A is equal to 3. That makes 4 into b squared. Again, that's going to be our b squared, because 9 was our a squared. And b would be 2. And if we use our formula, very quick and simple, remember that c squared equals a squared minus b squared. Or basically, 9 minus 4 would have been 5. And to solve for c, we just take the square root. C will be plus or minus the square root of 5. And again, plus or minus, because remember there are two foci. That distance is going to happen twice. So now, if we want to actually sketch, we just need to identify where will our vertices and our foci be. Well, thinking about a very simple graph, again, we've centered ourselves at 0, 0. We are going to travel, because A is beneath the y coordinate. Again, we're going to travel A units vertically. Y travels up and down. So again, we're going to have a vertical major axis. We're going to travel 3 units upwards from 0, 0. So our vertices will be 0, 3. And we'll also travel 3 units downwards. So 0, negative 3. So 1, 2, 3. And 1, 2, 3. We'll also travel b units left and right. So again, that'll be the minor vertex, or the not technically called vertices, but sort of the other direction. We want to travel 2 units left and right, because again, that was beneath the x coordinate, or beneath the x squared. And then finally, we want to get that focus on there, which again is root 5, or about 2.2-ish, right? Somewhere in that area, in that 2 point something range. So we're going to put our foci on here in the direction of the vertices, in that same vertical direction. The last thing to do is just graph our ellipse. Now, I'll give you a hint. One of the easiest ways to graph an ellipse is just try to make sure it looks fairly stretched out. Again, we've got our foci both traveling up and down, root 5 units. Right? But again, we want to travel sort of past that point. So an easy thing to do is sort of stretch upwards before you curve over. This isn't going to look perfect, but we want to try to go through those red points. Ooh, that was pretty bad. Let me try again on that last one. Maybe the last two, in fact. But again, we want to stretch downward before we curve over and up and out. Now, hopefully you can draw a smoother ellipse than that. But that's essentially how you would come up with the details for your ellipse. Now, one other tricky part is if they give us a general form equation. We need to convert it into our more helpful sort of rational looking, those fractions added together sort of equation equal to 1. So given this equation up here, the first thing we're going to do is we're going to move that 37 to the other side. Then I'm going to group my x's and my y's, and I'm also going to factor out. I want to get x squared by itself and y squared by itself so that I have the opportunity to complete the square. Go ahead and take a second and see if you can remember how to complete the square for both the x's and the y's, and remember to balance your equation. Whatever you have to put in there, remember you need to balance on the other side. Alright, so I've got those squares completed. Again, I knew that I took half of -6 was -3, but that means there must have been a +9 up here. 9 times 9, though, means I needed to balance with an 81 on the other side. Same thing goes with the green side here, the y's. Again, half of 10 is 5, squared is 25, but 4 times 25 means I added 100, so I need to balance with a +100. The right side ends up being 144. On the left, we've got 9. Again, we factor to those perfect squares, so 9 times x minus 3 squared, plus 4 times y plus 5 squared. And in the end, remember, we want to be equal to 1 for our formula. So I divided by 144. Simplifying, 9 over 144 is 1/16. 4 over 144 being 1/36. From there, we can judge the rest of our information. So we can say that our center then is at 3, -5. We know our A value is the larger value, so it'll be 6. B is our smaller, so our square root of 16 would have been 4. C, again, we would have to say A squared minus B squared, again, is C squared. So the square root of 20, or basically plus or minus the square root of 20. To get our vertices, now we have our center. Again, we're going to travel in the y direction, so vertically. So we've got 3, -5, but I'm going to add and subtract, so plus or minus 6. So we would have been 1 and -11. For the focus, again, same idea. We're going to be 3, 5, plus or minus that root 20. Or if you wanted to break that down, 4 times 5 is 20, so it's a 2√5. You could simplify a little bit, make that a 2√5. You could find those decimals if you actually needed to go graph, but otherwise, again, that's usually a pretty good, decent answer. Vertices, we probably should have simplified down to being a 1 and a -11. Remember, -5 plus 6, -5 minus 6 to define our vertices. And then we could make that sketch of our ellipse. I'm going to leave the sketching to you. But again, take your time, make sure you get it into this good form, remember to be equal to 1. If you need to rewatch the video, do so again. Otherwise, good luck, happy graphing.